Welcome to the WiDS Datathon second place winners call. This is Maggie from Kaggle. Turn it over to Sharda and then Wei.
Thank you. My name is Sharda Kadanidi. I'm a data scientist at Stanford Med School, and I was co-chair of the WiDS Datathon this past year. And it's my pleasure to welcome Kim to the second place awards discussion. Thank you.
And I'm Wei, and I work as a machine learning researcher at Harvard University. And this year I was co-lead of the WiDS Datathon with Sharada, and really excited to talk to our second place winner, Kim. So Kim, so maybe I'm going to ask you to introduce yourself and maybe a little bit of background, what you are studying, what you do for work, and then you can launch into anything that you want to share with us.
Yeah, I'm Kim Montgomery. I'm a data scientist at H2O. I did a PhD in applied mathematics. I actually did predictive modeling in the energy industry for about 4.5 years before this, so it's a problem that I know something about. And I'm a Kaggle Grandmaster. I've been ranked as high as 15th in the Kaggle overall. And H2O has had teams in the contest the last 3 years, and we had all-female teams the last 3 years, so I'm excited to be able to do a presentation again this year.
Cool. That's super exciting.
That's cool. And maybe you could talk about how things were similar and different from this year, since you're presenting again this year. And did the learnings from last year help this time? If you could also touch on that, that would be great. Go ahead.
Okay, yeah, I'll share my slides. So actually the data this year was fairly different. So it was kind of interesting to work with. It differed quite a bit from the hospital data that we looked at. So this year we were trying to predict for about 10,000 buildings in the test set, based on 76,000 buildings in the training set, what the annual energy usage would be for each of the buildings. And each of the buildings in the training and test set had individual building IDs. So it wasn't clear, at least at first, whether there were buildings that appeared more than once within the data set. So that was one of the things that I looked into early in the competition, was the possibility of buildings occurring more than once, even though they all had different individual IDs. And we were provided with 7 years of data, where the first 6 years was in the training set and the last year was the test set. So there was definitely a time series aspect to the problem, where from year to year, at least if you have the same building, you'd expect that the energy usage would evolve due to both evolving usage in the building, how their energy usage needs are changing, and also due to year changes in weather. And the data set contained quite a bit of weather information. So for each month in each year, there was temperature data giving the minimum, average, and maximum temperature. We also had some annual weather data, total precipitation, some wind information, some average temperature information, heating degree days, cooling degree days. We also had an Energy Star rating, which gave information about how energy efficient the building is on a 0 to 100 scale, where 100 indicated that the building was more efficient. And that turned out to be a really important feature. We had state information. There were a handful of states in the training set. Also a little bit of information about the facility type, what general category the facility was, the year the facility was built, square footage, and elevation for the facility. Yeah, so in general, when you're trying to predict energy, you have to think about both temperature dependent features, which are usually related to heating and cooling. On a hot day, you'll use more heat. On a hot day, you'll use more cooling, and on a colder day, you'll use more heat. And also non-temperature dependent factors based on what appliances might be draining power. Are you running a Bitcoin mining operation or something that uses a bit less energy? But in either case, we didn't have a ton of information about what might be present within the building. We had a general category indicating what type of building, what type of facility the building was, and whether it was commercial or residential. But we didn't have detailed information about what appliances might be drawing power or how that might be changing over time. So definitely it would be the case, since we don't have detailed information about what might be drawing power in the building. Uh, if you happen to have a past history for a given building, that's probably the best source of information for how much energy the building will be using in the future, because it's giving you some read on what's actually in the building drawing power in a given year. So one thing that I looked into early on is whether I could find similar or identical houses within the training set and test set. And I worked on that pretty hard. I tried different combinations of the features that we had for each building, and found that if you matched the buildings that had the same state, building class, facility type, square footage, and year built, uh, those seem to be pretty similar buildings with similar energy usages across the years. And just assuming that that's either the same building or a similar building seemed to be a pretty reasonable assumption. So I took anything that matched based on those factors and assumed that that was the same building or maybe a very similar building. But for a lot of the matches, I was getting exactly 6 matches, one for each of the 6 years. So it did look like it was probably the same building in a lot of cases, but there's a possibility I was just finding similar buildings. The elevation was one of the features that I played around with. I was getting fewer matches when I included elevation, and eventually noticed that that seemed to be the only thing differing for some buildings. So I found that if I threw out the elevation, I was getting better matches, and I was getting more sets of matches where you had one match for each of the 6 years. So that seemed to be a rather unimportant feature. In the end, with that matching condition, almost all of the buildings in the test set had some history within the training set. 9,067 out of the 9,705 buildings had at least some history in the training set. And that was pretty useful, since it's going to be the main thing telling you exactly what's going on for a given building. Especially if it happens to be the same building, but probably also if it's just a similar building. Yeah, and another thing that I noticed is you could use the temperature readings in order to define a more granular neighborhood than the state information that we had. So by keeping track of which houses, which temperature readings corresponded to the same house, and then matching houses that had the same temperature ratings, it was possible to define a neighborhood ID that was a little bit more granular than the state ID, and gave you a little bit more granular information about where the houses were located. Yeah, and so then I needed to decide how I was going to divide the validation and training data. This is plotting the average temperature that was just given in the data set. So average temperature for each of the geographic areas across the 7 years. And one really nice thing that happened to happen here is that year 7's the test set, and year 6 had a pretty similar distribution of temperatures to year 7. So it was fairly apparent that year 6 would be really good as a validation set. It was tempting to leave one to use cross validation and just leave 1 year out for each of the years in the data set. But since year 6 and year 7 were pretty similar, it was fairly apparent that using year 6 as the validation set was going to be probably a better idea for this, at least for this contest. And it was also convenient that year 5 is also fairly similar, since a number of the models used the previous year information. So it was really lucky that those 3 years were pretty similar. And also in time series data, it tends to be good to leave the last year out in general. So I did end up using year 6 as the validation set. Yeah, and in general, if I was developing a model, I'd just because you have these changes in weather that are sometimes, for some years, there are pretty drastic changes in weather. If I was starting over and developing a more general model, I'd probably want to use a rolling test set where the validation and test set aren't always the same year, just because uh, you could get strange weather years in the validation and test set, and you don't want your model to be picking up on a specific year. You want something that's going to work more generally from year to year. And another thing that I would have wanted to do in general is, in this case, we actually knew the temperatures in the test set. If we were doing a real modeling problem, we wouldn't know the temperatures. We'd just know what the average temperature is in the region, and we'd need to adjust that based on how we expect the climate to be trending over time due to climate change. So if I was developing this as a real problem, we'd also need to have that temperature model that takes into account average temperature and how we're expecting that to change over time on average. Yeah, but as far as this problem, it was really nice that the validation and test set seemed to be pretty similar, so we were able to get pretty good results using the year 6 validation set. And probably the second most important feature in the data set was the Energy Star rating, which was the rating telling you how efficient the building was. So it was a rating between 0 and 100, where buildings with larger ratings used less energy on average. And here I'm plotting the average value of the target energy for each of the 101 Energy Star ratings. So we can see both that it's decreasing, as you'd expect. In general, the more efficient buildings are using less energy. And also, it's really, really linear. And if you look at individual houses, that was also frequently the case, that there's a pretty linear relationship between Energy Star rating and the amount of energy being used. So the fact that that feature was that the target and Energy Star rating was a fairly linear relationship was pretty useful. We can also see for some of the lower and higher values, they seem to be a catch-all for the higher and the lower energies. So when I did the linear modeling, I was throwing out points that happened to have 0 or 0, 1 or 100, because they seem to be catch-alls for, they seemed to defy the linear pattern that I was looking for. Yeah, and as far as feature engineering, generally feature engineering is something that I'm pretty enthusiastic about, and I frequently spend a lot of the contests doing just more and more feature engineering to try to develop better features. But this time I actually didn't do very much feature engineering. We had a bunch of temperature features, but there were only maybe a couple hundred levels for each temperature feature. So I was worried that if I developed too many temperature related features, I'd just be overfitting, because there are only a couple hundred ways you can actually split the data based on temperature. So I'd expect that if I developing a lot of features for a feature that only has a couple hundred levels is just going to lead to overfitting pretty quickly. So I did develop a few features. For the monthly temperatures, I calculated some ranges like maximum minus minimum. I added the heating degree days and the cooling degree days. I don't think those features helped very much. I also wanted to be able to use the granular monthly data to come up with some feature that represents how hot the year was or how cool the year was based on the monthly data. So I had a couple of different genres of features that did that. One was calculating the total number of degrees above a certain value for each of the 12 months. So if the value was 80, it'd take all the months that had a temperature above 80 and add the number of degrees above 80 for each month. And I had a similar metric for keeping track of how cold the year was for each. So it was looking at the number of degrees below a certain value summed across each of the 12 months. And that was about it for most of the models. And as I'll get to in a minute, some of the models were predicting percent change between one year and the next for houses that did have some history. And in those cases, it made sense, since I'm looking at the change between 2 years, to keep track of the difference in some of the temperature readings for those years, and also the difference in the Energy Star rating between those years. But that was just for the models that were looking for percent increase for houses that had some history. Yeah, and categoricals were also a bit different compared to what I do much of the time. I'm usually either one-hot encoding categoricals if they have a small cardinality, or I usually use target encoding if they have a larger cardinality, like the neighborhood or the facility type. There were only a few features that were categorical: the state, the neighborhood, the facility type, and the building class. And I looked at both one-hot encoding and target encoding for those, and saw that one-hot encoding was outperforming target encoding, which is what I'd usually use for the higher cardinality features. So I ended up just one-hot encoding everything. And I think the reason that one-hot encoding was better in this case was there were some facility types that didn't have too many examples. And in this case, similar to the building ID, an example of what a similar facility what a certain facility type might be using in terms of energy was rather important. And one-hot encoding can pick up on facility types that only have a few examples a bit better than target encoding. So I think that's why the one-hot encoding ended up being better in this case. And if we look at the feature importance for one of the gradient booster models, we can see which features it's picking up on. It's picking up on some of the geographic features, some of the neighborhoods, some of the states. It's picking up on some of the facility types, mainly the ones that use more energy than others. The laboratories were fairly high energy, data centers, grocery stores were potentially fairly high energy. So it was picking off a few of the high energy facility types. It's also picking up on some of my features for temperature across the months. So the low features were indicating how cold a year was. The sum of the degrees below, the first one's the sum of the degrees below 20 across each of the months. And it was kind of interesting that it was picking up on the low temperature features, and it didn't pick up on any of the high temperature features, at least in the first 20. In general, I'd expect that the energy usage would go up for both higher temperature values and lower temperature values. So I expected to see a mix, but it looked like the model was more concerned with the lower temperature values in terms of predicting energy usage. And I'm not sure why that is, but it was pretty interesting. Yeah, so I'll get to the main model in a minute, but many of the predictions in the model involved gradient boosters. And I trained a number of different gradient boosters for variety and created various ensembles based on the gradient boosters. So the gradient boosters were either light GBM or XG boost. I tried different subsets of the features. Some of the models included all the features, and some I tried to get rid of as many of the temperature features as possible, just because I was worried that the temperature features might cause overfitting. I tried different targets. Some of the models were predicting energy directly. Some of the models were predicting the ratio of the next energy usage over the current energy usage to give a predicted increase or decrease in energy. And I only ran those models for buildings that had some history. And in both cases, I was getting rid of some of the larger values just to leave out the outliers um, and make it easier for the model to predict an average value. Yeah, which brings me to the final model. And again, most of the buildings in the test set had some information available in the training set. And the model that I used for an individual building in the test set depended upon what information was available for that individual building. In the best case scenario, for some of the buildings, they had a previous history, and it happened to be the case that the Energy Star rating was the same for both the test set and a value in the training set. So in that case, I created a solution based on the exact match in the training set, the energy of the exact match in the training set. And I didn't want to, I probably would have done pretty well just using the exact value from the training set that matched, but I wanted to adjust things a bit for temperature. So I used two of the temperature features, two of the more important features, to try to scale the most recent temperature reading based on the temperature difference between the 2 years. And then I also blended that solution with one of the gradient booster models at a 75%, 25% ratio. And both of those were just to try to include some temperature variation, because even though there's an exact match, the weather between the 2 years was varying. Yeah, and the second case was if you happen to have a building that had substantial information available, the number of points that were available for each building varied quite a bit. If the building had a substantial amount of information available in the training set, then because we know that there's a pretty linear relationship between the energy usage and the Energy Star rating, I tried to create a linear model for that individual building, modeling the energy versus Energy Star rating. And if that fit turned out to be good, I think I was using R squared greater than 0.95, and the Energy Star rating wasn't too far outside the values that were in the Energy Star rating for the test set wasn't too far outside the values that were in the training set that I was basing the linear model on. Then I decided that the linear model was a pretty good model for that particular building. And in the next case, if none of the previous cases applied, but the building did have some previous information in the training set, I used an ensemble of gradient boosters, which I talked about a little bit before, predicting the percent increase in energy between the most recent year and the next year. So I took the most recent energy for the building and multiplied it by the expected percent increase or decrease in order to scale based on temperature to get a prediction for what the energy usage is likely to be in the test set. Yeah, and some of these gradient boosters were trained using the Energy Star rating, and some of them were trained leaving out the Energy Star rating, but still using all of the data. And that's because not all of the buildings had Energy Star ratings. So if a building in the test set didn't have an Energy Star rating, I used the ensemble that was trained without the Energy Star rating, so it wouldn't be over relying on the Energy Star rating. Yeah, and the other trick here is there was a final check to make sure that the energy values for the same house didn't have too large of a range. If the difference in the maximum and minimum energy values was unreasonably large, I assumed that maybe I had accidentally matched buildings that weren't really similar buildings, and I didn't use this most recent energy scaling method for that case. Yeah, and the final case was if we didn't have previous information for a house, or we didn't have reliable previous information for a house, then I just did the simplest thing and created an ensemble of gradient boosters predicting the energy directly for that house. And that's probably one of the simplest possible models, just directly predicting the energy. But there were only 600 some houses that didn't have any previous history. Yeah, and one thing that's probably worth pointing out is that because of the fact that the most recent value for the buildings was a really strong predictor of what's going on within the house and how much energy is being used, what appliances are being used. Simply using the most recent value was a pretty strong model in and of itself. So if I took my full model and for the 9,000 buildings that made up most of the test set, just use the most recent value. And otherwise, for the other 600, I just left the value the same as my full model. I was getting a solution that would have been 11th place on the private leaderboard. So just using the most recent year's energy information was a fairly strong model. And that's probably because the most recent history was so important in making the prediction. Building in temperature values into the model, and the Energy Star rating information helped a little bit, but not really that much. If you figured out the energy rating and just predicted the most recent value, you had a pretty strong model for this competition. Yeah, and again, the fact that we only had one year in test and validation was a bit limiting. If I had, in this case, we knew that the temperatures were pretty similar for the last 3 years. But in general, instead of using the most recent year, it might be better to use something like the median of the last 3 to 5 years, just so that you're not picking up on a most recent value that happens to have really strange, anomalous weather conditions. Yeah, so what we found was that most recent energy was really a pretty good predictor in this case. And definitely the past history for the building was by far the most important feature in determining what's actually going on within the building and predicting what the future energy usage for the building was. The scaling trick that I used, multiplying the most recent energy by predicted percent increase or decrease, did help, but most recent energy was definitely the most important feature in the data set. Yeah, and that's about it. Are there any questions?
Yeah, thank you for a really thorough, high-level walkthrough of your entire, thought process during the competition. I think the other participants going to find it really useful. I just want to highlight that your final model, is a very sort of bespoke kind of model where you're really thinking about, case by case how you ought to predict rather than say one model, right, that handles a very general case. So I'm curious as to kind of like, is that your general approach to modeling? If you could say kind of like, just as part of your work, what is your general approach to modeling, tackling these problems? That I think will be really illuminating for other participants.
Yeah, frequently I do quite a bit of feature engineering. I just spend some time understanding the data set and thinking about what features would be important for a certain problem. Yeah, it's probably not the usual to have all these different cases, but in this case we had different houses with different amounts of history available, and different modeling techniques worked better depending upon how much history was available and whether they had that Energy Star rating, which was the second most important feature. So in this case, yeah, having different models really made sense.
Yeah. And I also love that you spend a lot of time emphasizing that understanding the data set is really important. And I generally think that it's undervalued, right? Exploring, understanding the data. So do you have any sort of general suggestions for folks about what to do when they're beginning the initial exploratory data analysis phase?
Yeah, generally simple things. Make a histogram of I'd make a histogram of all the features, look at the relationships between some of the features and the targets, and just spend some time getting a sense of what the data looks like in general, um, whether you're seeing anything as far as the distributions that you might look into. For categoricals, you probably want to look at the categorical levels and see whether some of them could be combined or whether all the categoricals match up between the training and the test set. Yeah, things like that. I spend a lot of time just visualizing the data at the beginning before getting started.
Yeah, these are super great tips. Sharida, I think you've got some questions about future.
Yes, for sure. I think just hearing you talk is really interesting. We've been really involved in preparing the data set. So from our standpoint, at least from my standpoint, seeing you like describe how you hashed or worked through the problems is really interesting. And that you arrived at like state and neighborhood and low temperatures. These are the grocery type, facility type. These are sort of very important features when we were preparing the data set. And seeing that you sort of arrived at a similar conclusion with your future importance, that's very good research. And if people wanted to do more research in this area, this is sort of a phase 2 kind of on this on building energy consumption. What aspects would you recommend that they work on sort of in terms of research?
Yeah, if I was developing a more general model, I'd probably want to look at different validation sets, and as I mentioned before, just how things are varying from year to year. I was basing a lot of my models based on the previous year, but those temperatures, those weather conditions happened to match up really well. So I got lucky and didn't have to deal with weather anomalies too much. So I'd probably look into how best to deal with weather. Do you want to look at the previous year that has the best weather match, or do you want to look at the previous year that has maybe the median of the last few years? I think you'd probably want to take into account both the weather conditions and both matching weather conditions and how close they are to the year you're trying to predict, because you have both you're trying to predict both changes over time and in what the energy usage of the building is and the temperature dependent effects. So I try to take into account both of those.
For sure, for sure. Okay, when we were preparing the data set, we actually brought together 2 very different data sets. One was the CCAI data sets, and one was the NOAA, the government data, which had a kind of a lot of zip code level data. So we had to join it at the zip code level. So that would explain some of the patterns that you observed, that you picked up on, that with the neighborhood neighborhood level. That's because we performed a zip code level joins, and which is what you picked up on. That was kind of interesting for me to hear.
I don't know that I have general advice, but definitely thank you for holding the competition. It was a fun data set to work with. It was fairly simple with a little bit of building information and some temperature information, but there turned out to be a lot that you could do with it. So it was definitely a fun data set to work with. And I'd like to thank you for sponsoring the competition again.
Yeah, absolutely. So I do have one final question. So, you are aware that we have phase 2 for the last couple of years now. So this is for folks who are excited about, the data set we put out for phase 1 and have some cool ideas, like you were saying, looking more into the weather or thinking about this truly in a more kind of like time series fashion, right? Where the dependence is like over multiple years. So with that being said, are you enrolled in phase 2 where we're taking deeper dives looking at not only energy consumption models, but other aspects of climate change?
I haven't enrolled in phase 2 at this point.
So I guess at this point, that would be my job to try to convince you to do so. So I mean, I understand that obviously, these things take time, but phase 2 also happens over kind of a very long period of time, all the way until the end of June. So we'd love, for phase 1 folks, especially folks who made really good headway on phase 1, to consider doing phase 2. At least check it out. I think that there's a lot more interesting problems in there for you to solve.
Yeah, I'll think about it.
I mean, the goal of phase 2 is more research. And since you've already done a lot of research, it's sort of open-ended to help people focus on research problems, go through the process of doing research and articulating their findings. So, it'd be interesting for if you think that there are certain observations that you might want to share in a research setting, that would be a good forum to do that. So we welcome that.
Yeah, it was definitely a cute data set, so I'll think about joining phase 2.
That's
Awesome. Great.
fantastic.
I have a question. When you participate in a WiDS competition versus another competition, can you tell a difference, or what are some of the differences that you see?
I don't know. There were quite a bit of advice for beginners on the discussion page. There were a range of different experience levels that might be a bit greater than a regular Kaggle competition.
Yeah.
It was tabular data. I'm thankful for that because I really love tabular, and we don't get that as much on Kaggle. So.
Yeah. We're an open funnel. So right now we've got a lot of NLP ideas. So it's kind of interesting.
Yeah.
Well, good.
That's by design. We do focus a lot on beginners, sort of breaking down barriers and welcoming women who have never done data science before. So that's part of our mission, to make data science and technical skills more accessible to women all over the world. So that's definitely by design. But we also want to have our competition, our framework platform available to both beginners and advanced people, which is why we have the phase 1 and the phase 2. But it's really wonderful to hear that you pick up on that as a contestant.
I enjoyed working with the data in general. As I said, it was a fun data set to work with. It's something that I've had some experience as far as energy data working with before. So I was happy to see a tabular competition. I was happy to see an energy competition.
That's great.
It was a good contest in general.
Yeah, absolutely. Well, Kim, thank you so much for your time. And we hope to see you in phase 2 and obviously in future years of competition.
All right. Yeah. Thank you very much.
Thank you very much.
Congratulations.
Congratulations.
Thank you, everyone.
Thanks.
Bye.
Thank you.